All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you all had a great weekend. Like, the weather was amazing this weekend. And I got to go to the Forks, and I got to go skating there. And I don't know if you have done this before, but I really love going to the Forks and skating on the river. Partly because it's just, I don't know, it's just fun to get out and go skating, but it's also fun to just see how much joy people are having there. Like, there are lots and lots of people that are going and skating what appears to be for the first time at the Forks, and like lots of people falling over and having lots and lots of fun and really, really enjoying themselves. So I don't know, I can't recommend that enough. If you have been skating at the Forks even this weekend, go back and skate more at the Forks. If you've never been skating at the Forks, but you like to go skating at the Forks. If you've never been skating before and don't even own skates, just go to the Forks. You can rent some skates, and it's lots of fun. And doesn't matter what skill level you have. There are lots of people that are at your skill level. It doesn't matter what skill level you're at. It's a lot of fun. I really, really like doing that. And so I was really happy to be able to go and do that this weekend. Let's talk about operating systems. So there's a bunch of stuff that I want you to be able to do by the end of today's lecture. The first thing is a review of Comp 2160. We kind of did a bunch of review of Comp 2160, but I want to really specifically review this specific part of this specific learning outcome from Comp 2160, which is the redirecting of standard input and output for file I/O. In fact, the really specific part of this really specific learning outcome from Comp 2160 is the use of standard input and the use of standard output. Those are the things that I want us to think about right now. We're going to be thinking about this a little bit this week in terms of working with processes. And then we're going to think about this next week in terms of how processes can communicate with each other. But I want to make sure that we're on the same page in terms of using standard input and output, what those terms mean, and then how that kind of fits into the structure of what we've got for code that we're writing. Then, for what I want us to do today, I want us to be able to write code that uses system calls to create a process. We're not really going to do any management of processes today. I mainly just want to be able to make a new process and then start to think about what that system call is, first of all, and then how we can work with programs that use the system call and how we can sort of like mentally model what this looks like as we're going through this. And then finally, the last two here are kind of related to each other. I want you to be able to describe the life cycle of a process. So in the textbook chapters, there are 3 states that a process can have that are described. There's running, there's blocked, and then stopped. Stopped? No. Ready, yes, thank you. Yeah, oh boy, I can't even remember the 3 states. In practice, on a Linux operating system, there's lots and lots more kinds of states, and we've actually kind of seen this already when we were looking at the output from PS, when we were beginning to think about processes. But I want us to be able to think about the life cycle of a process and how an operating system manages processes, the data structures, control of processor, and modes in the context of creating a process and in the context of using system calls that interact with standard input and standard output. So I want to think about all of these things kind of together today. So first and foremost, I would like to start thinking about standard input and output and standard error. And I kind of just want to do this in the form of a little quiz. So let's pop open our devices and take a look at this. I'll give you about 30 seconds to join. Sorry, I actually forgot completely about putting the QR code in this today. Does anybody know what that flag is? What country that flag is for? Is Sweden? Okay. I saw someone in Assiniboine Park yesterday putting a lot of Swedish flags, like tiny little Swedish flags along the road around where the duck pond is, and I wasn't really sure why. I still don't know why, but now I know what the flag is. All right. So the code should stay up there if you're not joined yet. Let's start the quiz. So some of this is stuff that you might have seen in Comp 2160, and some of it isn't. All right, okay. I'm using this partly as an indicator to see what you actually saw when you took Comp 2160. The last time I taught Comp 2160, I actually only barely showed fgetS, and I spent most of my time thinking about stuff like getchar. We did talk about fgetS, but we spent more time talking about getchar. Getchar is a good way to get a single character, as you might expect from its name. It reads from standard input. You don't pass anything to it, but you get standard input, one character from standard input. getC lets you pass a buffer and get a single character into it, and fgetS, passing one, and this stdin file pointer type lets you get one single character from that when you pass one as the count for the number of things that you want to get from that. All right, let's go to the next question. All right, okay. Okay, so this is something that is like the wool had been pulled over your eyes in Comp 2160 a little bit. So that's an idiom that kind of means like we're hiding the truth from you. We're hiding the truth from you. As far as we were looking at in Comp 2160, and certainly as far as we were looking at in Comp 1020, when you were making a new instance of scanner, for example, you always, at least whenever I do Java stuff, I say scanner keyboard equals new scanner system.in. That's how I describe this thing. Standard input is often the keyboard. It's very often the keyboard, but it's not always the keyboard. We're going to see this more next week, but it's not always the keyboard. Very frequently it's the keyboard, but not always. It's not the only way to get input for a program. And in terms of this answer, the thing that I'm thinking about here is we can read files. We can read files to get data for input for the program that we're currently working with. Standard input is a file-like thing. And what we have seen in Comp 2160 is that it's a file-like thing in the sense that that stdin variable is a file pointer. It's a pointer to a file, and we're passing that to functions like fgetS to get input. What we're going to see today is that standard input is also just a file descriptor, just an integer type, like we have had with the other open function that we've been working with in terms of getting file descriptors. It's a file-like thing. Okay, here's the next question. This is related to that one. Okay, good. You took the hint, yes. Standard output is also a file-like thing. When you were doing stuff with C in Comp 2160, you may have put fprintf stdout, where stdout was the name of a file pointer, but it's a file-like thing. I can write to it. I can print stuff to it. And again, as we're going to see today, standard output is also just a file descriptor. There's just an integer that represents what standard output is. In terms of the only way we can print output from a program, sort of like we can get input from a program on the command line using files. We can also put output into a file directly. So we could open a file and then write to that file if we wanted to. All right. This is pretty tight. Heartstorm. I like that. Okay. Here's the last question. Okay, all right. Standard error and standard output are both for output. They're just for output. Standard error ought to be bold and red all the time. Standard out is a file-like thing and standard error is not. They're both file-like things. They're both file-like things. There's an std error variable that you can work with that's a file pointer, and also there is a file descriptor that represents standard error. There isn't really a difference between the two of them. The difference is that they are different places that you can output to. They're two different file-like things, but they're ultimately the same overall behavior. The main difference between them is that everyone agrees that standard output is where you print most of your output, and standard error is where you print an error. But that's just an agreement that everybody has. There's no actual functional difference between the two of these things. All right. Okay, let's see who is at the top here. I kind of hope it's Heartstorm. Okay, Daddy. Congratulations, Daddy. Okay. All right. Okay, are there any questions about this before we move on to stuff? Yeah.
With redirecting input or output,
would you be able to print to standard input?
Would you be able to print to standard input? Like, if you change the file descriptor to whatever the standard input file descriptor is, right?
Yes. So what we're actually going to see, you may have seen this in Comp 2160 in the form of a pipe. That's that single, I don't know what the character is actually called, a pipe. It's like the OR, but you just do one instead of two. A pipe is a way to basically hook up standard input from one program into one program from another program, something like standard output. You can connect the two of them directly to each other. And the way that we're going to see this next week is with interprocess communication. And what we're going to see is that you can actually manipulate the open file table and replace what standard input's file descriptor is with a file or with another process's standard output.
But would you be able to do it with the same program? So like if you redirect standard input to be a file, would you then be able to write to that file with standard output as well?
Well, that's a good question. So basically, can you take a file and make it some program standard input and also its standard output? Yes, I think you technically could do that. I don't know what the outcome of that actually is, though, because it's not something I've ever even thought about, to be honest with you. That's a great question, and it might be worth trying after you know a little bit more about the system calls that we're going to use to change those values in the open file table. Remind me on Monday next week, and we'll try it out. Yeah, OK. Any other questions? Okay, awesome. So I'm going to leave Mentimeter here. And what I want to do is I want to write a little C program that does some basic I/O. I've started out with a template here. So I've put a link to this repository in today's lecture notes on the course webpage. And I'm going to clone this repository and start from this. And then any work that I'm doing in class today on these two files, I'm going to push to this repository after class. So if you want to follow along with me, and I recommend that you do, again, if for nothing else, then to get some practice, again, writing some C programs. It might be worth your time. So I'm going to clone this, git clone, and I'm going to paste that URL in here. And I'm going to change into this process management directory. Is that big enough for you to see at the back? OK, awesome. We're going to be working with this program to begin with. It's called basicio.c. Right now, this is just an empty template. There's nothing in here. It does nothing other than returning exit success, so it exits successfully as soon as it is finished. I want this to be a pretty simple program for now. So the program that I'm going to write is going to read a single character from standard input and then print that single character back to standard output. So let's start. I'm going to first declare a variable that's called buffer, and it's going to be of type character, and I'm going to initialize it to the null byte. I'm just going to give it a value, set it to 0, and I want to have this as a stack allocated variable. I'm going to print a message out, print f, enter a character, enter a single character, then press enter, or Control+D on your keyboard. I'm not going to put a new line because I want to actually be able to type the character in right after that colon. Then what I'm going to say is buffer is equal to getChar. And then I'm going to say putChar buffer. And then I'm going to exit success. Is this good with everybody so far? I'm going to save my changes. I'm going to pop open another terminal on the side here. I'm going to change to this directory. I'm going to make it, and I'm going to run it. Any suggestions for characters? F, F. I'm going to hit Control-D on my keyboard. There it is. I typed in that F, I hit Control-D, and it printed F. So now there's two Fs right beside each other. Yeah, that's awesome. This is really cool. This is a really excellent start to Monday. I'm going to bring this back in a second, but I kind of want to stop and wonder, like, what was the point of that exactly? I thought we were supposed to be talking about processes. I want to go back to this program, and I want to revisit this program in the context of a few different keywords, and I want us to start thinking about what's happening as this process is running. So the first thing I want us to think about is mode switching and system calls. We're going to use a program called strace to help us with this. I want us to be thinking about the state of the process. And we're going to inspect the state of the process with that PS program. We're going to use that same PS program to do this. And we're going to take a look at both of these in the context of really what's happening on each of the lines of this program. There's like 5 actual functional lines here. There's not much going on, but there's a lot for us to be able to think about in terms of this. So I'm going to go back to my program here. And what I'm going to start with is I want to think about the state that this program is in. So when I am getting ready to run this program, I hit // on my keyboard, and I type in basic IO here. As I hit the Enter key on my keyboard, what I'm doing is asking my shell. So my shell here is this program, and it is called Fish. That's the name of the shell that I use. When you're on Aviary, your shell is probably called TCSH. If you're using a Mac, I don't see any Macs. Is anybody using a Mac? You're using a Mac. If you're using a Mac and you've got your thank you, yeah. If you're using a Mac and you've got your terminal open, you're probably using ZSH or Z shell. If you're using a Windows machine and you've got Windows Subsystem for Linux installed, you're probably using Bash or technically Dash. When I hit Enter on my keyboard after I typed in this // and then the program name, I'm asking my shell to start running this program. The way that my shell is going to start running this program is I'm going to hand wave this just a little bit, but On line 4, our program starts. This is nothing new to us. Like, we've seen main at the very first class of Comp 1010. Main is the entry point to our code. This is where our code starts running. But what I want us to think now is, as I'm entering main, my program is running. It's in a running state. Instructions in this code are executing right now. When I go to line 6 here is going to be something like a store instruction or a load instruction. I'm going to assign a constant value to this memory location. On line 6 here, my program is running. It's running in its own space. It's allocating a variable. It's asking for memory, sort of, and it's putting a value in that memory location. On line 8 here, my program is still running. It's still in the running state. What we're doing with printf is we're making a library call, a standard library call, and we're asking for some text to be written to standard output. We're going to come back to that in just a second. But for this entire time, our program is effectively running. On line 10 is where things start to change here in terms of the state that our program has. On line 10, what we see as output from our printf has appeared on the screen, but our program right now is currently in Linux in this sleeping state. In terms of those 3 states that we had in our textbook, we are blocked right now. We are not able to proceed. So this getChar function over here, this line causes my program or my process to change states from running to blocked. We're going to get stuck here. Our program will never proceed at this point until whatever it is blocked on becomes unblocked. Unblocked here means that my program calls getChar. getChar just gets stuck here. It's waiting for something. My program will never get control back. It's never going to run any more instructions until we return from getChar. Once we return from getChar, so once I type in a variable here, a value in my terminal, and I hit Control-D, now my program, my process is unblocked. It's running again. After this line returns, getChar, the process is back in a running state. After we return, we're back in this running state, but when we're stuck on getChar, we are blocked. This is a word I'm going to be using frequently, especially as we get to IPC and interprocess communication. We are blocked. We cannot proceed. PutChar is, again, kind of like printf, asking OS to do something for us, to start printing stuff to our terminal, but our program is running effectively the entire time. So the state transitions here are, I'm going to start running at main. I am in the running state, and I'm running all the way up until I get to getChar. Once I hit getChar, I'm in the blocked state. I'm not able to proceed anymore. I have to just get stuck here, and I just have to wait around until I am unblocked. Once this getChar returns, so whatever it's waiting on is satisfied, then I'm back in the running state, and I can continue with running in my own process's address space here. We're okay with that? Okay. The other thing I want us to look at here is I'm going to use this program called strace. strace should be installed on Aviary if you're doing this on Aviary, and you should be able to run this on Aviary. You may need to install it on a Linux system if you have a Windows subsystem for Linux as a separate package. You unfortunately cannot use this on Mac OS. There is no strace on Mac OS. You would have to be running a Linux virtual machine to be able to use this, this program. So if you want to try this out with what I'm going to be doing in just a second, and you're on a Mac, you'll unfortunately have to do this on Aviary. But I'm going to use strace, and what I'm going to pass to strace is the program itself. I'm going to close this bottom terminal here, and I'm going to hit Enter on my keyboard right now. And immediately there is a ton of output from this program. What strace is showing us is all of the system calls that are being made as my program is starting. There's a lot of stuff here that is kind of outside the scope of our course, and it's not super relevant to what we're thinking about right now. So as an example here, this access at the top, open at, mmap we might look at a little bit later, pread, fstat, mmap, mmap, arch, prctl, set robust list, rseek, mprotect, munmap, get random, brk. We're going to look at some of these system calls, but all of that stuff is happening before we even get to main. All of that stuff is happening before we've even gotten to main in our own code. All of this stuff is beginning to happen in the standard library. All this stuff is beginning to happen in the standard library. But at a certain point, we do actually start executing code inside of our own main function. The first place that we start to enter system calls here in our own code is right at the bottom here. What we see is this system call that's called write. It takes 3 arguments. The first thing is the file descriptor that we want to write to. The file descriptor that we're writing to here is standard output. The number 1 is standard output for this process. This is the entry in the open file table for this process, and that entry refers to standard output. The second argument is these are all of the symbols. This is the array of characters that I want to write, or the data that I want to write. And the last argument here, this 54, this is the number of bytes that I want to write to this thing. So printf here is a wrapper provided by our standard library around the write system call. What's happening here in terms of that idea of mode switching is that when I call write, I am going to basically relinquish control of the processor. So my process is running. I have allocated this memory for buffer, and I've assigned it a value. There are no system calls for that because this is something that's happening in my own process. When I call printf, the standard library is wrapping this around write. Write is a system call, and now I'm actually asking the OS to do something for me. In order to do that, we have to go through this whole process of doing a mode switch. Mode switch here is from user space. This is where my process is running to begin with, to kernel space, kernel space, the OS level ability in terms of modes that we have in our processor. My operating system is going to take this stuff that I've got here, and it's going to act on that now. So it's going to take the data that I've passed, and it's going to find the open file table entry, and it's going to start putting stuff into a buffer for that specific file. And then eventually, write is going to finish, and it's going to return control back to my process. We're going to switch back to my process, and we're going to mode switch back into this user space for my process that I've got here. When we get to line 12, so once we return from that, we're going to do a mode switch from user space to kernel space, and then back to user space. On line 12, we're going to call getchar. And the same thing is happening here. Getchar is a wrapper around the read system call. Read right now is, I would like to read from file descriptor 0 which is standard input. So that's file descriptor 0. That's the number 0 in the open file table. I'd like to read something, and I am blocked. I'm stuck. My process is blocked, but I've done a mode switch to the kernel space, and the kernel is kind of just sitting there waiting for us to type something in. It's doing lots of other stuff right now, like my web browser is still open, and it's keeping track of the time, and all sorts of other things are happening, but in terms of my process, it's just stuck, waiting for some kind of input from this thing. So if I type something in here, I'll hit F, and then I'll hit Control D on my keyboard again. At that point, what we get is, it's done the read on standard input. It's read one single character. And this 1024 here is representing how many bytes I've requested to read. Yet char is actually asking for a whole kilobyte of stuff. But my kernel says, here's 1 byte. Here you go. That's all you're going to get, because that's all there was before this buffer got flushed out to me. When I hit Control D on my keyboard, what I'm telling the operating system ultimately is, I'd like you to send whatever's here to the thing that's requesting it right now. So the same thing is happening when I press enter. It's just take whatever's here and send it to the thing that, that's asking for it right now. So once the read here is complete, we're going to do this mode switch back into our user space, back into our process here. We're going to assign that value to buffer. So we're going to do this store operation. We're going to put this either into a register or to somewhere in memory in this address space. When we get to line 17 here, we'll do the same whole process again, just like we did with printf. I'm asking my operating system to print this single character. And so we're doing this write system call. Put char is a wrapper around the write system call. We're passing the file descriptor number 1, which is standard output. We're passing a buffer that has that 1 symbol in it, and we're passing the number 1 here to say, I'd like you to write just 1 byte to this thing. So we do that mode switch. The operating system takes over. It puts that F into the buffer for standard output, and then it returns back to us. It returns control back to us in our address, in our mode. So we're going from kernel mode back to user mode. And then on line 19, we are effectively done here. And at that point, we actually also do a mode switch again back to the kernel space, back to the operating system, and the operating system will do the whole clean up everything for us process. And then control returns back to my shell. So there's another mode switch here from the kernel space back to user space, but it's not in my code anymore. It's in my shell's code. So we're making these transitions between different modes every time we're asking our operating system here to do something for us. Printf is this wrapper around write, getChar is a wrapper around read, and putChar is a wrapper around write. And at each of those, we're doing system calls, giving control back to the operating system, mode switching, and then coming back into our own address space here. We okay with that? Okay. What I want to do now, we can revisit this in a little bit, but what I want to do now is I want to start thinking about how we can begin to actually manage processes ourselves. So far, our shell has been managing processes for us. And the way that our shell is doing that ultimately is we type in the program name that we want to run and we hit enter on our keyboard, and that process gets started on our behalf. What I want to do is write a new program that launches a new process. When we're doing this, I want to think about a few different things. One is the process ID. We've seen this idea of process ID before in the output from PS, so process list. There are IDs that every one of these processes gets. I want us to think about the relationship between these two different things that we've got, a parent process and a child process. And then I also want us to think about what happens when we do things like making changes to values in one of the two processes. But before we get there, let's start by writing some code that just launches a new process. So I'm going to go back to my terminal here, and I'm going to quit out of this program. And what I'm going to do is I'm going to start editing this process management.c program. So far, this is the same sort of thing. There's not really very much going on in here, but I'm going to make a change to this program immediately. And I'm just going to ask you to blindly accept the change that I'm making. And then when we get to some more stuff later, we'll see what's actually happening here. The change that we're going to make that I want you to blindly accept for now is that we're going to change the arguments to main. We're going to change it to something that looks like what you've seen before maybe, but it's not exactly what you have seen before. The first thing is going to be argc. This is something that you've seen before. It's an integer. The second thing is a character pointer called argv, and it's an array of character pointers. You have seen this before? Yes? Yes? Some of you? Yes? Yes. Okay, awesome. Then we're going to add a third argument here that is another character pointer, and we're going to call this envp. Just accept it. Just accept it for now. We're going to see what's going on with this, but just accept for now that there are 3 arguments to this main function. It's the same thing. It will be called in the same way as far as we care about right now, but this will become important later when we're working with more stuff related to what we're starting to work with here. So just blindly accept this for now. The first thing I want to do with this program is I want to print out hello world. So far, nothing exciting is happening here. I'm printing hello world. This is the first program that we wrote in Comp 2160. I'm going to make it. And what I'm actually going to do here is very quickly, I'm going to put some stuff up here. I'm going to say void argc. So what I'm doing, just to be clear, I'm getting all these unused parameters, errors. I've set warnings to be errors here, and wextra and wpedantic are saying it's a warning to not use variables that are passed as arguments to a function. I don't really want to use these variables right now, so casting them to void effectively uses them to suppress the warning and then therefore suppress the error that we have. So I'm just going to say void argv and then void envp. Okay, so I'm going to make this one more time, and I'm going to run process management, and it prints out hello world. Like, this is the same stuff that we've seen so far. Now what I'm going to do is I want to introduce a new function call. The function call that we're going to use here, or the system call that we're going to use here, is called fork. To use fork, I have to include a new header, unistd.h. So I'm going to add that to the top here. And what it returns is a type PID t. PID here is process ID. PID is process ID. I'm going to declare a new variable here, PID t, my PID. I'm going to say my PID is equal to fork. I'm going to quit the manual page. I'm going to make this program. It's going to warn me that I'm not actually using it. It's set but not used. So I will void my PID for now. I'm going to make this. I'm going to run it. Nothing has changed. OK. I'm going to change this slightly. I'm going to delete line 17 here, and I'm going to print f. My process ID is, actually, I'm going to change this slightly. I'm going to say the process ID, the PID returned from fork is %d. OK, I'm going to make this. And I'm going to run it. And now we got 2 lines getting printed out after that. On line 13, we have one process. We are printing the words hello world new line to standard output. On line 15, we are saying system call. I would like to conduct a mode switch, and I'd like the operating system to duplicate me, please. Duplicate me. The idea here is that our OS on fork, our OS is going to duplicate the current running process. This one. Duplicating the current running process means duplicating the process control block for this process. The process control block includes things like the open file table. It includes things like the current set of values that are in this program in terms of the memory that this program is using. And it also includes things like the current instruction pointer, the program counter, where I am currently executing code in this program. The fork function itself, I'm going to write this down, returns twice. I don't really like that because it's a weird way of thinking. It doesn't return 2 different times. It's just that now there's 2 copies of the same program that are running starting at the same point. It feels like it returns twice, but it's just 2 programs that are now running. The reality is 2 processes are currently running. Both are executing code starting from the same spot. So when I call fork here, what's happening is we do this system call and mode switch. When we do the mode switch, the registers in our processor are saved by our hardware, so it keeps track of what the current instruction pointer is. So for example, that. Our operating system will continue to operate in its own mode. It will duplicate that process control block, including the value of the registers, and then it will cause both of these processes to be running. It will do mode switches back into both of them. I'm going to add one more thing to this, and what I want to do is I want to see what's happening with each of these programs, so I am going to cause them to block. I'm going to cause them to block by calling getChar. I'm not going to use the output from that. I just want these 2 processes to get stuck here. I want them to block so that I can begin to inspect the state of these 2 processes. I don't care about the output from getChar. I just want to block. Just want them to block. So I'm going to make, and I'm going to run process management here, and we're stuck. There's 2 processes now that are blocked, and the way that we're going to check this is with PS. With PS, there are now 2 processes here that are called process management. I'm going to change this slightly. I'm going to hit Control-C on my keyboard here. I'm going to do printf hello world. I'm going to do getChar. I want to block just before I do the fork. Make, run it. We are blocked just before we do the fork. So on the output from PS, what we see right here is that that process is blocked right now. I'm going to go back up to that terminal here, and I'm going to hit Enter on my keyboard. When I hit Enter on my keyboard, we will unblock from here and proceed to the fork system call. Now that we've proceeded to the fork system call, 2 processes returned, and both of them are doing this printf, but they have different values for that process ID thing. And they are both currently stuck on getChar. They're both in this blocked state. So if I do PS one more time here, I've got these two processes. There's two copies of process management here. Their process IDs are 1231539 and then 1231574, which happens to be the same as one of these values here. One of the values that was returned from fork is the same as the process ID for one of the processes that we've got. We've got two processes here. The parent process is the one that called fork. So when we were looking at the output here from PS on this line where we had just one process, this is the parent process. When we had two lines of output here, our child process is this other one that showed up. When we're working with fork, the way that we tell the difference between these two processes is by looking at the value that comes back from this. I'm going to change this from myPID to just PID. What I'm going to say here is if PID is equal to 0, we are executing in the child process. The return value from fork is 0 for the child process itself. It's non-zero. It's the process ID of the child in the parent process. What I'm going to do is compile this one more time. I'm going to hit Control-C, or I'm just press Enter there. I'm going to compile this one more time. Right, I've got to change this. I'm going to compile this one more time. The last thing that I want to do here is I would like to make changes to a variable that's in this program. I'm going to declare a new variable. I'm going to call this letter, and I'm going to give it the value of W. In the child process, I'm going to say that letter is equal to, letter please? C, all right. Letter is equal to C. I think it's C with printf and just one R on letter. I'm going to make this one more time, and I'm going to run it. So we're blocked right now on line 16. We haven't forked yet. We haven't caused this process to be duplicated. I'm going to hit Enter on my keyboard to get past that. We called fork. We made the system call. We did the mode switch. The operating system said, OK, I'm going to duplicate you, and I'm going to cause both of these processes to be in the running state. We're going to do a mode switch back to these processes, and they are both going to continue. The parent process, when it's running this line, PID is not 0. It's the process ID of the child process, the one that got duplicated by the operating system, the copy of us. So in the child process, in the parent process, this conditional block is not going to execute. In the parent process, we're going to proceed immediately to this line. So the PID returned from fork is 1231878. This was printed by the parent process. The parent process will also print out the value of letter is W. And that just happens to be the order that it's in. The child process is going to start executing code in here. The PID that returns from fork in the child process is 0. So we've duplicated this PCB, and the value that we put into this register or this memory location is 0 for the new child process that we've created. in the new child process that we've created, we've also got this extra statement that says, change the value of this variable in the child process. Both the child process and the parent process then continue here. The child process is going to print out the PID returned from fork is 0, and it prints out the value of letter is, and in this case, C, because in the child process, we did make that change. What I want to do next class is I want to draw a little bit of this out in terms of what our OS is doing. Seeing this in code, I personally find this to be kind of mind-blowing and numbing at the same time. Seeing how two different things are coming back from one function call is a really weird idea. But when we think about this in terms of duplicating PCBs and current instruction pointers and stuff, it will help to see that as a picture. So what I want you to be able to do at this point is you should have a good sense of this idea of standard input and output. Again, this was from Comp 2160. You should be able to write code that uses a system call to create a process. You should be able to write code that calls fork. You don't have to do anything with it, but you should be able to write code that calls fork. You should be able to begin to describe the life cycle of a process, and you should be able to begin to describe how an operating system manages processes. And we spent most of our time here talking about modes, but control of processor, and then data structures are something that we have started to talk about today, and we will continue to talk about on Wednesday's class. That's it for today. Thank you all for coming out, and I'll see you on Wednesday. Bye.